talk about safe paths like for the first 10 minutes, and then you can take over.
Yeah, sounds good. Yeah, take your time. I think SafePaths is the most urgent project here, so we should take your time on SafePaths first, so no rush.
Yep. And,
so hi, everyone. We're actually live. So I think on the right side, we have Kaushal. I think you are a project manager for SafePaths, right?
Yep, I am the partnerships and funding lead for SafePaths.
Yeah, and then we have Praneeth, who's going to present SplitLearning, also from MIT. And then we have myself from Ocean Protocol. This is one of our webinars for COVIDathon, a Decentralized AI Hackathon, and the team at MIT, they're working on a really exciting project that they want to share with us. And we invite our participants to later follow up and join work on it. After these two presentations, we'll have our friends from Enigma presenting their approach. And then we'll have, again, a round of team building. Let's see how it goes. So, Kaushal, I think first we go with you. You can share your screen. I'll minimize myself and Praneeth for the moment.
Yep, fantastic. Can you see my screen?
Yes.
Okay. All right. Great. So, hello, everyone. My name is Kaushal, and I'm on the SafePaths team. And sort of just as a matter of introduction, I am an engineer. I did my bachelor's and master's in electrical engineering. And currently, I work across Asia and Africa on malaria elimination strategies with the Clinton Foundation. So implementing policies, pilots, tech-based pilots, and implementations. And right now, I'm a student at the Harvard Business School. So I'll just walk through what SafePaths is and just give a brief introduction, and then hand it over to Praneeth, our tech genius expert, who will walk through the nerdy details of privacy preserving algorithms and stuff. So what is SafePaths? It is basically a community, a whole movement that it has turned into, and our aim is to do contact tracing that is free, that is open source, that is privacy first, and like privacy is embedded in the design principles for everyone. So for healthy citizens, for patients who are diagnosed with COVID or any such disease, and for public health officials. And the whole idea is to reduce fear and flatten the curve, sort of reduce the burden on healthcare system, while preventing a big brother surveillance state kind of a response to the pandemic, which we've seen in a few countries over the world. And so, like, if you think about the very big or the large picture, the short-term sort of health goal is sort of improving digital tracing for public health, which is related directly to the COVID-19 response. In the medium term, we want to restart the socioeconomic activity in a sustainable way. So think about when you go out of the lockdown situation in countries like Italy, like a lot of things are going to change. So how can we use this movement to restart socioeconomic activity without a lot of disruptions and distress? And the ultimate long-term goal is to make our societies resilient. So how do we ensure that our society and our communities are prepared and equipped to tackle these type of disruptions? So it could be like pandemics, it could be other disruptions, it could be a lot of other catastrophic events. So how do we build resilient societies in a way that does not give a lot of power to a particular state or an entity? So this is the large picture that we're aiming for. Today, I will focus on the first short-term goal, which is the immediate need of the hour. Like I said, our design is privacy first. And when I think about privacy, it is really 2 or 3 levels. So like I mentioned, a lot of governments across the world have resorted to smartphone-based tracking applications for pandemic infectious trail tracking. However, what this has resulted in is basically the personal liberty and privacy of citizens have been compromised. And our strong belief is that there is a better approach to this problem in a way that kind of preserves privacy of everybody involved and kind of solves the problem as well. So if you are a citizen, if you're a healthy user, the way we implement it is like all your location data, we use GPS trails, and we're going to be implementing Bluetooth data as well to help you figure out if you've been at risk or not. So all your information is currently logged on your phone. It does not leave your phone currently. The data never leaves a user's device unless they become ill, unless they are diagnosed. So if you're diagnosed positive with COVID, you go to a health official, who is the government official or whosoever the health authority is, and then you consent to giving or sharing out the location information that you've been in the last 20-25 days. And then the health official who basically trusted, will be given a web tool to redact out all the sensitive information and release totally anonymized information and aggregated information for the public good and public benefit. So at no point in the whole process, your privacy is compromised. And like I said, in the raw form, your location data is never ever released out in the public domain. We've done a lot of thinking on this, and this is a white paper that we've written. If you're interested in like what are the principles that we base our work on or solution on, I would strongly urge you all to read this white paper. And if I talk about the three main tools that we have, like for any pandemic, it's trace, test, and treat. We're focusing on the first one, and there are a lot of people who are focusing on the other two, but today I'll focus on tracing. And contact tracing is pivotal. I mean, it has proven to be effective in case of pandemics, any pandemic. And traditionally, how it's been done is like manual interviews. So you literally go to a health facility. Back when the Spanish flu occurred, we had a lot of interviews, or any such diseases in non-tech world. You have manual interviews, and that's prone to a lot of errors. For example, in South Korea, there was this one particular patient, 31, that went in contact with over 1,000 people, and the authorities had to manually go and interview and analyze over 1,000 people to find the infected trails. We think that leveraging technology, this could be done in a better and a faster and a more efficient manner, and without building a surveillance state. So I'll just talk about the tools that we have available on both sides. So Safe Places is a web tool that's available to the government officials. So, and then there's the other tool, other app, which is called PrivateKit, which is a user application, which is an Android and iOS application. It's out in the Play Stores today. So this is the web tool, and this is the PrivateKit app. I'll talk about what each of these tools do. So here, Safe Places is just a simple web tool, can run on any server out in the world. You just need a browser. A patient will share his or her information of a time-stamped location trail with a public health official, and then the public health official opens up this tool and loads this information, and then deletes all the sensitive information. For example, if I were the infected patient and I would have like my home, my personal private home and other places which are sensitive and I don't want to release out in the public on that location trail. The public official can easily, with a very user-friendly interface, just click and remove or redact out all the sensitive information. So you have load, save, redact out all this information, and then whatever is helpful for in the interest of public health, they can publish it out for the public good. And this app, this tool basically is out and it completely works. We have the tech team who tirelessly worked on this, and it's ready for use. And the motivation for this was just to enable the health officials to give tech-based tools and replace this manual interview traditional process. It is privacy preserving and meets the US privacy standards. The other part of this is the PrivateKit app, which is basically an Android iOS app. It's out on the Play Store, and it's a logging tool. So you can think of this, you can imagine this to be your own personal diary, which is where you log your location information. And every 5 minutes, it will log your location information and safely, securely store it on your own phone, right? So it's a three-phased approach. We are now in version 2. So the first one was it will just allow you to log your information on your personal phones, and then the diagnosed patient can choose to share the history with the health official. So if you were to get sick, rather than saying that, hey, I think I went to these places in the last 20 days, you can just pull out this app and say that, hey, here's my location history, and you'll get all the information here. So that's version 1. It was released, I think, in the Play Store on 14th or 15th of March. We've gone through multiple revisions. It's out and live. Version 2 here is where the real magic comes in, where the health authorities, the publicly released information, is going to be compared with your own personal trail, and basically a contact tracing will be done. So the app will tell you whether you were in contact with an infected individual by intersecting these trails. And the computation is either going to be done on the phone, which is very, very secure because it happens on your phone, or it is going to be done in a complete end-to-end encryption with mathematical guarantees of security. And I think Praneeth will touch upon some of these things later. And then the third version, which is a little bit into the future, is basically using these encryption techniques, split learning, and enabling direct notification. So complete decentralized system without the need for like third-party access to any of the individual redacted location trails. So that's the broad ambition. We are currently in rapid development of version 2. Just a very simple illustration of how it works. So step 1, patient goes, instead of relying to the memory, they share their location data to the health official. Then the health official basically uses the SafeTrace web tool that I showed you, and then redacts out personally identifiable information and then publishes out. And step 3 is that once trail is released, all users who came in contact with the diagnosed patient will be notified. Again, data never leaves the phone in this situation. The roadmap here, like I said, the phase 2 is currently active development. And right now we're working with a lot of government authorities across the world to deploy the solution. It is ready to be deployed in multiple countries across Central America, Africa, Europe, Asia, and so on. So we're in very advanced conversations with a lot of country officials getting interested in implementing these solutions. And the app is also being translated into multiple languages. I think 15 to 20 languages. It's already there on GitHub. It's all open source. It's on GitHub. So feel free to play around with it and develop interesting folks and tools that are helpful to the population. The third one, I said, it's based on using cryptographic techniques, which is currently, again, under development, but more like in a research phase, and Praneeth would be the right person to talk about it. Just giving a little bit intro on who we are. So we have an amazing team of super talented people, a bunch of epidemiologists, medical experts, scientists, researchers, policy experts, and implementation experts, global scale-out experts. So we've been in active conversations with WHO, IDARE, HHS, which is the US Healthcare Authority. And we have great experts. So Sandy, Kent, Kevin, these are all world experts in different fields. We also have some of the AI experts and some of the world's most renowned encryption experts on the team. And the community is composed of volunteers with affiliations to MIT, Harvard, Mayo Clinic, Ernst & Young, some of the ex-Googlers, some ex-Facebook folks, who are all volunteering their time to build the solution. We also have some active partnerships with some of the open source projects that others have built in, and they're also contributing to this project. So it's open, free for all. So no matter where you are in the world, no matter what your expertise is, you're free to join our team. Feel free to visit our website or email this address, and you're more than welcome. I think we have over 600 volunteers now, and it's just growing day by day. We have, I think, around 4,000 people in the email list already. So, like I said, there's a bunch of countries, some of them in Europe as well, that we're working with for the implementation. If you have any questions or anything, feel free to email or I think post on the dev boards or whatever the best way is, and happy to take those.
Mm-hmm. Kaushal, if you don't mind, we have a couple of questions. Can we quickly go through the top voted questions? Okay. Thank you for the presentation. I have one from myself. Maybe I think a lot of people might have the same question. What's the critical mass, like the minimum density of users that you need in a community for this to be useful?
So I think we've run some models on this, and I think the models say that even 10% of the users, if they use it, it's going to show good results. Not the best results, but I think it's going to show good results. And I think Ramesh has been quoted in some of the newspaper articles also saying that. I think we've done a more scientific analysis on this as well. But I would be lying if I knew the exact numbers or the model numbers. But we have epidemiologists doing these models and running these through. But I think roughly the benchmark would even if 10% people use and download it, it's going to be useful.
Mm. Okay, and we have some questions around the open source availability. So our co-organizer Robin shared your GitHub link. It's github.com/triple-blind-market/private kit. Is that the right one?
Yes.
So we answered that. And if I understand correctly, you do welcome people forking this, adding features, but then kind of staying in the same ecosystem, right?
Yeah, I mean, we would love to know what you built on top of it and just spread further. I think I shared the MIT. I mean, it's the MIT open source license, so some of the details there. So if you can share that with the community, more than welcome. If you have some great ideas to build on top of this, again, more than welcome. So the ultimate thing, like I said, would be to use this contact tracing technology as a tool and then build applications on top. So if you think about it, public health is just one fork, right? You could have it being used by a lot of businesses, merchants, transactions. So you could think of a lot of for-profit organizations using this platform. So something like a Linux, Red Hat kind of an ecosystem. You use this technology, free to use, and then you do whatever you want that makes life simpler and helpful for people around the world. And these could be great hackathon projects.
Yeah, that's exactly why we thought it would make sense to collaborate instead of just reinventing the wheel from scratch. People will get an email tomorrow that will include links to your project, OpenMind. We have a presentation tomorrow from Andrew around the same time. So I'll quickly go through the next couple of questions. They say, actually, I think it would be better to keep this one for Praneeth. Let me look at another one. So someone's asking, this protocol relies on health officials doing the redaction. Is that correct?
For the first two phases, yes. So currently, yes, because we don't want to make it decentralized and then cause panic. So that's why we are going for controlled releases now. But if in the phase 3, that dependency would reduce eventually. And Praneeth will talk about using the technique. Yeah.
Okay, so I'll keep that in mind for Praneeth. So are there any guarantees that precise location will not be extracted? And there was a related one that how do you blur the kind of path, the location? If you want, we can also keep that for Praneeth.
Yeah, I think he would be better equipped to answer, but yes. So the location data, like I said, it never goes out of your phone right now. So it always stays on your phone. I mean, if it is shared, I mean, it's a simple, it's literally a click, and all the location data that's shared, the exact format is, I think, a JSON file. It just has lat long and the timestamp, lat long timestamp. That's all it has, no identifiers, nothing at all. So it's just literally a list of lat long in one column and a timestamp in another column. That's it. And then you can visualize it on a map using SafeTrace tool, and then delete out all the things that you think are personal to you. So.
Got it. And a last question, can people have access to this presentation somewhere? This is being recorded, so that's one way for everyone. But
yeah, I would say just access the recordings because we're evolving very rapidly. So
I see. Okay.
Changing. And I think if we tomorrow we have an all hands, our team is doing an all hands, so you're welcome to join that also. If you just join the mailing list, you'll know like when, I
Oh,
think it's
okay.
1 p.m. So they will share some updates, which might, like, again, tomorrow something might change. So I don't want to share a version that's not the most updated. So, but
yeah, that makes sense. Thank you, Kaushal. I think we'll move the rest of the questions. It looks like it's better for Praneeth, and I'll share. Praneeth, you can. I'll bring you to screen.
All right.
Kaushal, if you want, you can.
Yeah, but I'll stay for like 5 minutes and then.
Okay, please.
All right.
So you can start.
All right. Yeah, let me share my screen. Yeah, that was a very important topic that Kaushal was talking about, given the COVID situation here. All right. Hello, everyone. I'm kind of excited to see so many people in here. The last time I remember, there were like 183. I don't know what the number is right now, but that's great. So Kaushal gave in a very interesting discussion about the topic of contact tracing, which is highly relevant. And especially private contact tracing is certainly a project we're very much involved in right now, of how you could find these intersections between people's trajectories. So taking a step back from there, this thing about split learning that I'll be talking about is more of a platform for doing resource efficient distributed machine learning, of which privacy is one of the challenges that we're interested in, to look at privatizing this platform. So split learning, just like federated learning, are some very interesting possibilities for doing distributed ML. And when you talk of challenges like privacy, it would take it into interesting directions that could build on top of split learning or federated learning. So some of our code for split learning and getting started sort of tutorials are out on PySift. It's very relevant tomorrow that we have Andrew Trask from OpenMind. So these are the ones that build and maintain and continue to evolve PySift and PyGrid. So that's exciting. A little background about our group. It's led by Professor Ramesh Oskar at MIT. And we call our group Camera Culture, but our current tagline that has evolved over the time to catch up with current projects is basically making invisible visible. So we work on projects in terms of imaging inside the body, projects with respect to objects around us, but this talk is more on around the invisible data that we have all around us because of the siloing away of data that we see here. So the constraints basically are the data is siloed all over the world, and there's these very critical constraints of privacy and data utility that are kind of dueling against each other. So there's this sort of a dichotomy. Now, obviously, we would love to be on the top right, where you are able to squeeze out the most utility out of this data. So this is, I'm sure, a very common screen that you guys would be using on your phones. So I'm not saying anything negative about Apple in here, so don't get me wrong on that. This is just to set some context. There's great things that you have in terms of utility in current day world when data is distributed and data sharing is being done. So that's great, thumbs up. But there's also, this is just the tip of an iceberg. This is a wonderful article. You should check it out in New York Times of what could go wrong. And this article basically shows the tip of the iceberg of examples over people being tracked to great detail where their individual privacy is lost. And it could have implications not just at the individual level, but also at the regional, national, or the global scale. So this is a serious topic. So it's certainly a motivator for how we'd like to take about this. And it also has heavy economic implications if things go wrong in terms of privacy, as we keep seeing often again and again in terms of the amount of leaks that we see in terms of data and the economic loss that it causes. So just to be clear, we want to state our goal, which I believe is also a common goal for many of you people participating here. So how can we effectively enable individual, organizational, regional, national, and global collaboration through data and intelligence sharing without infringing privacy, security, safety, trust, and regulation? So there's three key things here. One is collaboration at different levels. There's data and intelligence sharing, and there's making sure the constraints are satisfied. The other unspoken thing is how can we do it effectively? So you don't want to spend all your data plan or spend a ton of dollars on maintaining data centers, for example. How do you make sure it can trickle down right down to the edge devices up to the larger devices? So this is the setting, and that's the website, by the way, for that's the project page. But for the code, you can reach out to us, or you can also look at the tutorials that are open source on PySift. A little more context before we get into split learning. This has been our trajectory around the invisible data style efforts and the data sharing efforts. We worked on AutoML when AutoML was a hot topic. We are currently looking at distributed ML and privacy. We're also very interested in incentives, so data markets, which is what is the incentive for people to share data in the first place, even if they have this privacy guarantees offered to them to do ML. This is our ICLR paper for AutoML, which is kind of fairly popular, I would say. And this is, by now, it's a very, I think forms a good meta approach that a lot of people still follow, which is how do you use RL to make sure you do this architecture search. Moving on into split learning, what else is out there? So we got data anonymization. That is not a good idea because there's been leaks, not to small firms, but really large firms that believe that anonymization is good enough and they release data. One of the earlier examples was Netflix challenge for the recommendation systems, the $1 million prize. That was anonymized and released, but the privacy was revealed because people just joined it with a publicly available IMDb sort of data set. So there's many examples of anonymization not being enough. It's a good pre-processing, but it's not enough. So then there's, so we're again looking at the utility and then the data protection. So these are the two trade-offs you're looking at. So if you think of differential privacy, which is certainly an amazing approach and theoretically very well grounded in terms of guarantees, and especially in terms of worst case guarantees that you would get, even in terms of any single record not having to lose its privacy. So the way this works is basically by obfuscation with noise. So people look at the query that you want to privatize, and then they want to look at the sensitivity of this query to outlier behavior in your data. So if there was a minority data point, which was in some sense an outlier to a data set, what would be the sensitivity of this query with or without that minority being present? So how much would the answer change, and would that reveal anything about the minority? So you want to measure the sensitivity, the classical approach, and then add enough noise to be able to cover up even the most sensitive perturbations to the output of the query that you could observe. So that's differential privacy. And actually, these dots are moving up and up. There's more differential privacy going on around training as well. So I should actually update the slide. There's more papers that are doing that for a while. So these approaches are giving you different levels of utility. So obfuscation, you can infer you're also being able to train the model, but the issue is the amount of noise that you need to add to get these worst case guarantees. The utility of your model is way far from what is desired, especially in this day and era of deep learning, where the models, at least in some domains, can perform exceedingly well. Even in those cases, the drop in accuracy is not very much appetizable. So there's still more room in how to go better on this trade-off curve. Then there's this extremely high protection kind of mechanisms, which are basically coming from the crypto community or the theoretical computer science community. So there's homomorphic encryption, where you convert data into ciphers, you apply operations, your result of your operation is still a cipher, and only once you decrypt, you get the answer that would have been the real answer if you did not even encrypt your data. So everything's extremely encrypted, and you have these one-way functions that are really hard to break. So that's homomorphic encryption, and then there's similar approaches in here that are highly secure, such as multi-party computation, where you're breaking your data into different shares, and no single party can try to figure out without complete collusion in terms of what is being transmitted. And then there's garble circuits and oblivious transfer, which are all different mechanisms within MPC. So there's this extremely strong approach, but the problem here, this is still true as on today, the dot I would still put it here is, the problem is it doesn't scale well computationally, especially for tasks like ML, where you want to train really large models with millions and billions of parameters in them. So it doesn't scale enough well computationally. We're not there yet. It's okay for small scale inferences, but not really large inference models. And also in terms of communication efficiency, for example, MPC would require many rounds of communication to do even operations that are on the simpler scale in terms of how complex the operation is. So where we are working and operating, along with federated learning, I would put somewhere here, but there's also possibilities of kind of pipelining and pushing this more towards the right in terms of the privacy by combining some of the other more private approaches along with the positivity of what split learning and federated learning offers in terms of utility. So of course, it's an ongoing research landscape. So that's the whole point of sharing these slides, so that those that are not aware of all the buzzwords will hear about them. But for those that have already heard about them, I'll share something more new in the coming up slides. So this is the general setup. So you got clients and servers. So what does federated learning do? Because we believe split learning has been inspired by federated learning, and we also consider it to be a variant of federated learning under some circumstances. So what's happening in federated learning for doing distributed ML, as proposed by these folks, Brendan McMahon and Yakub from Google AI, a couple of years back, is every individual client trains their entire model. So there's no data sharing. They're just training on their own data set. So far, so good. So there's some ensembling kind of an approach where the weights of the models that each individual client has learned are sent to the server. The server does a weighted average. The weights are just based on, the weighting for the average is based on how much data was used or contributed into the ecosystem by any model. So if this client used a ton of data in relative comparison to the other clients, this would get a larger weight. So you're kind of averaging models in here. So one thing, if you think another step into this, one obvious question would be, hey, every client is training a good model by itself, but then you're averaging these models. So aren't you going away from what a good model is, right? So if I draw a bunch of lines and if I average it, it would not explain. The average can certainly be much away than what individual models are, depending on the variability of their updates. So that kind of shows up during the convergence. Federated learning typically takes much longer to converge. Another thing to take note in here in terms of resource efficiency. These models can be extremely large. Most models today at least have millions of parameters, but if you push the limits and go to larger companies and look at models that are really large transformers or really large models like gpipe, these are also getting into billions of parameters, that kind of a regime. So the amount of communication of doing these uploads and downloads of millions of parameters is not as efficient as one would desire. Also, the edge device, the devices here may not necessarily always be a large company. That's why I said it could be at the distributed entities could be at the individual level, where it could just be a cell phone, your iPhone or an Android or whatever your favorite phone is. And there's certainly current day world, there's not enough capability on a cell phone to train a very large model without having to do some tricks or doing some partial inference or transfer learning. But if you want to do a full-fledged training, we're not there yet. So computationally, if you're putting the same load where every client needs to train the exact same model, however large it is, it's not very much possible as you keep going towards the edge regime. But it could also be at the global scale or the regional scale where it's still okay. So federated learning is still a great approach. It depends on what regime you're operating in within distributed ML and what your constraints are. Similarly, as you see, the pictures look kind of similar. So moving to split learning, what is different in here? It's kind of very simple, yet a reasonably elegant idea that gives a lot of benefits. So why not just do it if it's such a simple variant? So the high level, the idea is we don't copy the entire model across every client. We basically chop up the model. So this is the split part. You can split at different parts of the network, and you can split in different topologies of what you could do after splits. We will talk about that as we go along, but this slide is at the highest level what's happening. So you split the model in some form, and the pre-split part of the model or the layers are with the client, and post-split is with the server. And also, just to be sure, we're talking about the client server, like the leader follower kind of regime here. But split learning could also be seen in other setups or topologies of the network, like, for example, something like a Tor or like an onion router, where there's sequential splits and then it's hopping from one part to the sequence to the other. There's not necessarily a server. So there are different ways of operating this, but this is the most vanilla form that's worth looking at first. And so here, for this obvious reason, we are not now communicating all the weights of the model, which would be in millions or billions of parameters, but we're only communicating activations from one layer, which is a much, much tinier fraction of what the communication would be in federated learning. So that gives you the communication benefit, but also depends on some other parameters in terms of what regime you're in. We'll discuss that more. So I'm not saying split learning is always communication efficient than federated. There are different regimes under which one is more communication efficient than the other. But when it comes to compute and memory, I can definitely say that split learning is certainly a lot more compute and memory efficient on the devices, because as soon as you keep splitting, you're just doing another level of parallelization where the amount of processing that needs to be done on the client is being reduced depending on how early you split. So there's that. Then there's a little more inner detail of what happens, because here, as you see, if everyone's just performing independently, how can you make sure that one particular client is making updates on the server that is also palatable for the other clients? Maybe it's making a very greedy update that's good for that particular client, but it's not very useful for the rest of the clients, which means it's messing up the model for others. So there's some amount of synchronization, but you'll see those details in this slide. So it's still the same picture. So there's the client's Alice's and there's the Bob, the server. So the way it works is you're paying in having to synchronize a little more in this architecture over federated learning, but you get the benefit of having a lot more efficient performance from communication and compute and memory perspective. So what is the sequential nature I'm talking about here? It is that, say, Alice 1 works with Bob, does its forward and forward pass and the back prop. So that's done with Alice's turn. And Alice needs to synchronize its local weights with its next Alice, or whoever this next Alice is. These Alices could be, the order of Alices could also be chosen in an anonymous, in a more crypto fashion. There are protocols for that too. But this is the bigger picture. There's this level of synchronization that you need to do in terms of the local part of the model. And then there are other topologies that you can look at in terms of split learning. This is the Boomerang or the U-shaped thing. So here, the constraint is it's not just the raw data that is not being shared by the clients, which could, for example, be these different hospitals, but it's also the labels, because especially in things like healthcare, in domains like healthcare, labels are also extremely private, because that most often are the diagnosis of what the patient suffers or does not suffer from, and which is also extremely private and protected by law. So we don't want to share the raw data in terms of features, but we also don't want to share the raw labels. So there's a Boomerang style split learning where the beginning and end layers are with the hospital, the front and back, but the intermediate layers are with the server. So you basically have two splits, front and back in here. And it's a lot more straightforward if it was something like a DenseNet or ResNet, which are still awesome models. But if it was one of those networks that are even more popular in medical imaging, like the UNets, especially given their segmentation abilities, and their popularity in medical imaging, there is this issue of skip connections that this architecture has, where intrinsically by design, the architecture would need to communicate by skipping connections between the front and back layers. And these connections could be long or could be shorter skip connections. So in that case, you need to be aware of how you're splitting, because you don't want to split the connection. Then you're kind of breaking that communication or kind of making it messier. So if you were splitting much early and much later, then it would still fit in. The intermediate layers are with the server, the front and back layers are still with the client. So the data goes in, label comes out, both at the client, but the middle layers of the processing happens at the server. And yeah, so this is more deeper detail, so just a number. So there's other possibilities in terms, as we were talking about topologies. So you can have the vanilla setup like you saw here. Of course, everything in here can be done with multiple clients, and that's what we do. You can have the Boomerang setup. You can have some sort of a vertically partitioned setup where client 1 has some features, client 2 has some features, and you're merging it going around. And most of the tricks that you would typically require is possible. You could have like a multi-hop split like in Tor. So it's jumping from client to client to client, and so on and so forth. So this thing is one of the earliest experiments we did on like 500 clients in the distributed setup, but most of it was still a simulated setup of distributed. We are doing some really hands-on experiments, mimicking some even more realistic scenarios for split learning with Andrew Trask's team. Andrew's going to be talking tomorrow at OpenMind. We are very much in touch with them on doing some of these testings further. This is a fascinating topic of understanding the resource efficiency of these different distributed ML techniques and different constraints. But in general, the big picture is we see that split learning converges much faster. It also is extremely efficient in terms of communication and compute, especially the data. This is the data transmitter, this is the compute cost. So a few other things that basically that need to be taken into account is, even if the costs are lower, it may not necessarily mean that the time is lower. That's the reason we need to do a full-fledged study, because there could be, since there are some synchronization issues and sequential nature to split learning, there might be an overall delay in the process being completed relatively on that front, because there is some synchronization going on between clients. And there may be people waiting for clients waiting for other clients to finish their job. It's like a relay, basically. And if all runners in the relay are fast, then you're good. But if there's one that is blocking it up, you need to make sure how you're dealing with the stragglers to make sure the overall system is not hurting. So there's the finer details that certainly need to be simulated that will make it even more realistic in terms of the plots there. So we've studied the communication efficiency in these papers as well. And the big picture here is in setups where we have a very large number of clients and the model that you're using is very large in those setups, and especially if the data being shared per client is low, that's when we see that split learning is way more communication efficient than federated. And the other way around, it would be federated would be more efficient, depending on how extreme a case you are going into with respect to split. But for compute and memory, split is always more efficient. And we're also looking at combinations, like I was talking in the initial slides, between other approaches for privatizing and doing secure computation, along with distributed approaches like federated learning and split learning. So we are actively looking at combinations of these two. One of our approaches from our lab itself on the privacy front has been in terms of preventing reconstruction attacks, which is once you do the communication to the server, can a threat inside the server be able to reconstruct the raw data of the client? So we want to prevent that, because the data during the communication is encrypted, but once it's at the server, it's decrypted, and it can certainly have a lot of information that can reveal a lot of things about the raw data by itself, or some statistics about the raw data. So what can we do to squeeze that information out so that the reconstruction attack that the server does is not good enough to go back, but it's good enough to go forward to do the classification? So this is, I would call it, so one-way functions are very popular in cryptography, but I would call this kind of an approach here more like an information theoretic security, where you want to make sure the amount of information in going forward is way more higher than going in the reverse direction. So this is a non-cryptographic one-way function that you want to learn from a learning perspective. And then there are other attack schemes as well, attack designs as well, which we are also beginning to look at. But today I'll just show some results from reconstruction attacks, the one that I talked about in the setting before. So
by the way, Praneeth, if I may jump in, how much more do you think you will go?
It would be another maybe 2-3 minutes.
Oh, okay, perfect.
Yeah. Thank you. Talks, yeah. I'm just showing like a couple of results and that's it. Yeah. So we want to look at what the adversary can reconstruct in terms of the raw data by interjecting or from being an adversary at the server itself. And if you did nothing about it, even at the first layer, there's a lot of leakage, obviously, about information about the raw data. But if you do our approach of decorrelating the communication that you're doing with respect to the raw data, you would see that it's extremely hard to reconstruct. So these are some of the results of the reconstruction, which would not match the reality that you see in this slide now. So this is the reconstruction that you get after approach using state-of-the-art pix-to-pix image translation models. And this would be without our approach. And this is the raw data. So it's really hard to infer what the raw data would look like from our reconstruction. So the attacker would not be able to reconstruct the raw data, basically, nor would he be able to figure out things like ethnicity or gender or age, which could be very sensitive topics. So jumping on the math part ahead, I want to show in a couple of slides in terms of two things. One is, can we reduce the communication further? The communication rounds further. That's a great challenge question. Can we come up with newer architectures that are hybrid of split learning and federated that probably does something of that sort? Secondly, there's certainly many more challenges in this area, which is if the data per client is very low, federated would not be able to handle it, because if each cell phone is giving you 5 records of data, you cannot train a large model on 5 records of data, but which is still okay with split learning, which is great. But there's some challenges that even split learning doesn't solve, like for example, can we make the communication bandwidth even more lower? Can we push the limits of compute even further? One very important challenge is how can you deal with data that is extremely non-homogeneous? So if the data from one client is very different from the other, how do you make sure the model converges? And so on and so forth. So that's a laundry list. And this is our last slide before I share a couple of links. So we're also looking at model selection, which is there's clients that have data in today's world, and then there's these powerful servers like large companies that have really large models. The server doesn't want to share the model, the client doesn't want to share the data, but how do you make sure these things work? And how do you know you're triggering the right model for the client's data? So we have an approach for this. We call it the expert matcher. We are working on this rigorously and expanding it daily on a day-to-day basis. So there's that. And there's some announcements. We are starting an alliance for distributed and private ML, given our interest in our group. And we welcome people from industry and freelancers and volunteers of all sorts, along with academic researchers to partner with us. So feel free to reach out to us.
Praneeth, do you have a link for this alliance?
Yeah. So So if you go to the project page, the splitlearning.github.io, you will see some information, but you'll see a form in the end for contacting us. So just contact us on that, and we'll share more information directly. In terms of the finer details, because alliances have more legal binding around them, depending on what kind of alliance is being proposed. So so we rather appreciate a proper form being filled up and then we reach out back.
Got it.
Accordingly, yeah. Of course, there's tons of people working with us, and this keeps changing day to day. Okay, last slide. I'm not sure if this is going to make you laugh, but I still need to give my attempt. So there's there's certainly something called doing splits, which are very hard. It's worth trying them if you're flexible enough, given the work from home days that everyone's in. But that's certainly not split learning. And if you want to learn about split learning, go to our website. Also try our tutorials on PySept for split learning. And we also have some internal non-PySept code for split learning as well. You can reach out to us about that too. That's it.
I think if we could hear it, you would hear like claps for everyone.
Yeah.
But thank you for the amazing presentation. I also brought Ainsley from Enigma to screen, so we'll go through a couple of questions. And Ainsley, if you also feel like you want to answer, definitely jump in. So many questions. I'll try to be efficient. There was a question around when you say that the paths are blurred, what precise protocols are you using for blurs?
Protocol for which one? For the
I think it's about private kit. So like
okay.
maybe it's not a protocol, but
Yeah.
no, I think they mean protocol, not crypto protocol.
Yeah. For private kit. Yeah. So split learning is for risk assessment post private kit. How can you assess the risk once you've done a contact trace? Because you still want to reduce your false alarm rate, even if you did a proper understanding of who came in contact with the infected person. It doesn't necessarily mean that he would get infected. He came in contact doesn't necessarily mean he will. So you still want to reduce the false alarm rate and use your resources optimally. So that's where split learning would help to do a statistical model or like an ML model that, if it is private, can do risk assessment of doing a better prediction of people that came in contact, looking at their demographic data, all kinds of private stratified data. In terms of the contact tracing itself, how to do private contact tracing. So we are looking at protocols based on private set intersection, where you have this grid cells and you're trying to figure out how you can do a common intersection between two sets of grid cells to see which are the indices that got turned on between the infected and uninfected. But that's one approach. So there's also a lot more other cryptographic protocols that we are working with, along with the crypto professors at MIT, the list of names that Kaushal was sharing in his slide. So there's some insider information that I'm not sure I can release yet or not. But yeah,
it's a small group. You can do it here.
There's certainly, I would say it's still a crypto-based approach. We released this paper, which might be of quick interest for you.
You can share it in the chat if you want.
Yeah, I will do that. Yeah, I'll put the link. So this is not for private kit, but this is some parallel work with private set intersection for doing contact tracing.
Okay.
But this is not what private kit is implementing. So just to be sure. So we have other schemes that we are also doing from a crypto perspective for doing this private contact tracing, which is basically intersections of trajectories.
Got it.
Yeah,
I think Google also released the research around private set intersection a while ago. I'll share a link to that too. So I'll ask another question. This is a really simple question. If SafePath is using Google Maps or OpenStreetMaps?
Oh, I think that's a dev question.
Okay.
I think it is Google Maps, but I can check and confirm.
Okay. And then Robin asked if the split is done after non-linear layer in the network, is the data reconstructed?
Yeah, the networks are nonlinear, heavily nonlinear. So if you did nothing about preventing privacy, then data can be reconstructed. If you just did split ML, split learning is a good platform for distributed ML in an efficient way. It's not a private ML. It's a good platform to build private tools on top of it. Just like federated is not private by itself. It's only doing a good thing that they're not sharing raw data, but that doesn't mean you cannot reconstruct back with either approaches. So with our decorrelation approach, we do see that you cannot reconstruct. We tested it rigorously. We're also looking at differential privacy and homomorphic styled approaches for split learning too.
Got it. One last one, by the way, Ainsley, if you have questions, also feel free to ask.
Sure. Do we have time to talk a little bit about what we're doing, or do you?
Of course. Yeah.
Yeah.
So I think if Praneeth, if you don't mind, I think it was great having you. Please stick around if you can, if you don't mind. We'll go through their approach at Enigma. They're working on SafeTrace, if I'm not mistaken. So we'll do that presentation, and then we can do another round of questions.
Yeah, I might have to go in and out, but
Okay.
But for now, I'll be there for a while.
Yeah. You can turn off your video. So Ainsley, the stage is yours.
Okay.
Quick intro. Ainsley is from Enigma protocol. Okay.
Sorry, my dog is attacking me. Coda, go. Dad, can you come get the dog? Got more coworkers in the house than normal.
Okay.
Sorry, go ahead.
Yeah. But by the way, Praneeth, I think you kicked yourself out. You can come back in if you want, or I'll do that for you. So Ainsley is from Enigma protocol. If I'm not mistaken, your approach is with trusted execution environments.
That's
in general.
Right. We use trusted execution environments for the compute.
And you will tell us a little bit about your approach and this project, SafeTrace. I'll share the GitHub link in the call to action so people can directly go there too.
Cool. Great. Thank you for the intro. And thanks, Praneeth, for the very in-depth presentation. It was super fascinating. I will go ahead and share my screen so that you guys can see. Great. So yeah, I'm Ainsley. I work at Enigma. We're also a team that was out of MIT a few years back. We work primarily on privacy preserving smart contracts in the blockchain space, but we've started working on this SafeTrace effort about 3 weeks ago, obviously due to the need that we saw for this. I won't spend too much time defining contact tracing because I know we've been over that in this call already, but we have seen a few different countries start doing this approach, Israel, Singapore, and China. And it's also been used in the past with other pandemics such as Ebola to really effectively follow the path of a viral infection. This is also something that is much easier now with the plethora of data that's collected by smartphones, which are pretty much ubiquitously carried. Just to recap, contact tracing basically follows where you've been and who you've been able to come into contact with. It's also important that there is testing available for this to be an effective strategy. One of the things, of course, that we noticed at Enigma is that a lot of these approaches are not adequately privacy preserving. And you're dealing with really sensitive data like your location, who you've been in proximity to, as well as information around your health status, whether it's symptoms or whether it's test results. That's PII information and it's quite sensitive. For organizations that keep this data in a centralized location, this puts a pretty onerous security burden on that organization to keep that data safe. So that's sort of a situation where you may have a single point of failure if that's a government organization or an NGO that's holding on to that data. In some implementations also where we've seen most user data is staying on the edge device, it still often requires data about people who are tested positive for an infection to be collected and then pushed out to those users. Another approach that we've seen is anonymization, but we also have seen in the past that even when data is attempted to be anonymized before it's shared, especially location data, that's often not actually adequate for many scenarios where you can actually identify that person, especially if you have other types of data on where you can intersect the two data sets. One of the other problems with contact tracing that's problematic is that if you have many different applications that are doing this, say I'm using one application, my brother's using another, my friend is using another, if these applications are practicing successful data privacy, then it's going to result in them not being able to share data between each other, which means that unless you have one application that everybody's using, you're going to kind of have this balkanization of apps, and they're not going to be able to be as effective because you're not going to be able to share that information with one another. So those are kind of the two big problems that we wanted to solve: bringing these data silos together, as well as making sure that the data is private on the back end. So SafeTrace is not, it's really sort of a back-end storage and compute service. And it exposes an API for any type of client application to interact with. And then it will basically enable you to use trusted execution environments in order to perform simple computations over that data, basically to find whether you've had, whether your places that you visited have overlapped with people who visited those places and who have tested positive according to certain parameters. The way that this works at a high level is basically that various applications that do collect things like user data or Bluetooth data can send that information to the SafeTrace server, which is where the code is being run inside of a trusted execution environment. And then depending on the computation that's being performed, you either can get back an individual view, which basically shows you the different types of some information about the places where you have overlapped with individuals who've tested positive, or a global view, which is more basically performing heat map computations inside of an enclave and then returning basically the what's that word? Some information around the heat map that doesn't provide individual data points. I forget it's a centroid. That's what the word I'm looking for. It returns centroid data for the heat map instead of individual points.
Okay.
Yeah.
That's your version of blurring, right?
So we are not working on this global view right now. We're kind of in the research phase for that. So I would say yes, that's the version. That's the equivalent approach that we would take when we start to work on the global view. For the MVP that we're currently working on, that we're providing for the hackathon, we're focused a little bit more on the individual view. But for example, working on that global view would be a great hackathon project.
That's great to know. Thank you.
Yeah. So just a little bit of background, because I know we've talked about a bunch of approaches to achieving privacy. Here, what we work with is something called a trusted execution environment. And these trusted execution environments are essentially regions inside of memory inside of a computer that basically generate their own key pair, and that even the person who controls that computer is unable to see the data that's being submitted to that black box, that enclave. And so what can happen is, as part of the process of certifying these, which is called remote attestation, an application can ensure that the trusted execution environment is both legitimate and hasn't been tampered with, as well as verify what code is actually going to be executed when the data is sent into that enclave. So that's a process that you can think of like as somewhat analogous to like an HTTPS certificate.
Can I ask a quick question here? But the data should be transmitted from somewhere to this TEE, but like, so whoever is implementing these solutions should also take care of encryption during transmission, right?
That's right. So the API provides the tools that are needed for the application to do encryption client side, and then send that data to the enclave. So the flow is it's a Diffie-Hellman protocol, and the API provides the necessary information for the client app to do that. So basically, location data or any type of sensitive data should never leave the client application unencrypted. So it's encrypted client side, and then sent to the trusted execution environment where it's decrypted within the enclave. And then the computation is performed and the results are returned encrypted back to the user. So as I mentioned briefly earlier, the two views that we're starting with here are an individual view, which basically lets you see, it's a simply like matching algorithm that looks at your location history and matches it with people who've been in the same place within a time threshold who've tested positive. And as I mentioned earlier, we're also exploring like using a heat map algorithm that can produce centroids and kind of place those on an app so that we can get more granular information than we get right now from sort of like municipal reports while still preserving privacy. One of the interesting things about the TEE technology that we're using is that if someone wanted to use our system to create another algorithm, they would be able to. So it's somewhat arbitrary in that sense. Now that person would have to kind of make sure that that algorithm was sufficiently privacy preserving, and then they would have to kind of launch their, they would have to redeploy the remote attestation for that, but it is a little bit more flexible than other solutions. So, in the long run, like if these views aren't meeting the needs of public health officials or researchers, it's possible to kind of redeploy with new backend analysis without rebuilding everything from the ground up. So with that, giving you a little bit of high-level context, I'm going to turn it over to Victor, who I think is also on this call. Victor, maybe you can say hi in the chat so we can get your handle. And Victor is going to basically demo what we have so far, and then we'll briefly talk about what we're hoping to get out of the hackathon and how you can basically, if you're interested in contributing to this, get involved.
I'm inviting Victor to screen now.
Cool, thank you.
It's Victor with C, right?
Victor Grauserat.
I'm inviting a Victor. I hope it's the right one.
Yep.
Hi,
Yes,
Victor.
this is me. Thank you.
Yeah.
Wait, and how do I share my screen? Yes. One second. Okay.
By the way, apologies to everyone for the timing. That is, I think we're like at least half an hour over time, but I hope you're enjoying this, and I see more people even joining us. So let's go with Victor's presentation.
Great, thank you. So I'm going to pick up here from where Ainsley left it, and we have a demo of the technology that we are making available for this hackathon right here. So hopefully you can see my screen, and I can make some of those terminals bigger, but I need these 3 terminals on the screen. So on the top left corner, I have what would be my client. And then on the 2 lower windows, I have the things that are running on the server. So this is a server that it's right now we are hosting on IBM Cloud, and it's a special server in that it has to have SDX capabilities and SDX enabled. And also I want to clarify that these 2 terminals at the bottom are extremely verbose right now, but of course once we deploy this for real, there will be no output here. So these are only going to be verbose for demo purposes. And the right lower corner, this is the actual enclave that I'm starting now, and it's listening on a socket using inter-process communication to talk to a JSON RP server, which I'm launching on the other screen. And this is the one that actually interfaces with the outside world. This is a server that, again, will respond to JSON RPC queries. So if you try to visit this page with your browser, you get an error because this is actually what I expected to see, a 405, because the method is not allowed. You cannot get requests, HTTP GET requests on this server. You will only be able to get post requests using JSON RPC format. So let's try to get one of such requests to the server. The first one I'm going to do using the terminal and just curl. So I've copied here for convenience, and I'm pasting this. And what this does is that reaches the server where we are running the enclave, and is asking for the method get enclave report. So if I send this, a lot of things are showing up on the screen. So basically, when I send this request, the JSON RPC server received the message, passed it on to the enclave. The enclave generated a quote, send it to the Intel IIS servers for remote attestation. Intel verified that this code is running inside a legit enclave, produced a report stating so, which is it's encoded here, and the enclave sent it back to the JSON RPC server, which included the report itself, which here is base64 encoded, included the signing key of the enclave, which is, well, this is a public key of the signing key of the enclave that only the enclave knows. Like, we don't know the private key of that key. IBM does not know it. No one knows it other than the enclave. So it's a pretty neat technology. And here there's a signature of this report using this key that you can use to validate that all this makes sense. And this is at the end the request or the response that I'm getting back from that request. Now, this is just to sort of prove the communication back and forth, but now let's get to the specifics of the application that we've built here. So we are loading data that looks like this. So for any user that we are tracking, we are entering latitude and longitude and a start time and end time when that user was at these two coordinates, and whether the user tested positive or negative for coronavirus at this time. Right. So here I'm doing this with JavaScript, and I have a script that will add this data to. Oh wait, 1 second. Sorry, I want to reset something. Remove the. Okay. I want to make sure that I start from an empty state. 1 sec. Let me clear the window. Yes, I need to restart this one. Okay, so I'm going to add data for user 1, which again is in this format, and in this case, I'm only going to add these 2 data points for the sake of simplicity. And what happens here is I'm going to run it. It happens fairly fast. Oops, something's not wrong. Oh yeah, okay. So what happened here is that, and I'm answering the previous question where first I'm requesting an encryption key to the enclave. The enclave received that request for the key and put out a public key from which the user through Diffie-Hellman generates an encryption key, a symmetric encryption key, and uses that to encrypt the user ID, and encrypt the data. So what we are seeing here is the encrypted version of these 2 data points. And I'm also including my public key so that the enclave can correlate it to the request that fulfilled before, generate the symmetric key on the enclave, and decrypt. So that's what the JSON RPC server received. I'm missing. Oh, no. That's what the message received, and then the enclave received it, decrypted, and this is what the enclave received and stored in memory first, and then on disk in encrypted way. So on the real app, we won't be able to see this, but knowing that the enclave had received that data. So I'm going to do the same thing for user number 2. It's funny because obviously in the demo it goes way slower, but this goes fairly quick. Again, and then the enclave, you see how it received the data for user 2 and added to the data that it had. So now that's what the enclave has inside that no one can see, except for now we are running on debug mode. And so we have user 1 and user 2 data safely stored inside the enclave. So then I have one last function that I can call, which is find a match. And what this will do is that so user 1 is healthy. It tested false on both times. And here I have user 2 that tested positive. And the algorithm will look that for the user that I'm querying, in this case, user 1, is there a match in terms of space and time with anyone who has tested positive? And the coordinates in one case, it's hard to see, but on the second point, they are the same and around the same time, and so I expect that I will get one match. So when I request the match, no, find match. I'm gonna clear a little bit this screen and this one. Again, at first I request the encryption key, and with that encryption key, I encrypt my request, which in this case is just only the user ID, and the enclave receives the request, decrypts the data, finds a match, and encrypts the output so that only the requesting user can see the match. So this is the encrypted output, which passes through the JSON RPC server, and this is the same encrypted output in hex string, and only the client is able to decrypt and get the match for his or her points that match someone else's who tested positive. And here it says false because this is data from user 1 who always tested false, but at this time and at this location, he or she was in close proximity with someone who tested positive, but we don't know who that is for privacy-preserving reasons. So that concludes the demo, and I'm passing it back to Ainsley.
Thank you.
Thanks, Victor. And if anyone has questions for Victor, like, please ask them while we've got him, and he can be able to answer you kind of about anything that's happening inside of the enclave or our encryption process. So what Victor just demonstrated for you, I'm going to actually just show you on our GitHub page right now. So this is the repo that we have this project in. And what Victor just demonstrated for you, basically,
your screen is not shared. We have to.
Got it. Okay, sorry. That will make it much easier. Okay. This is the repo that we have this code in, and what Victor is showing you is basically the algorithm that's being executed is running inside of the enclave. This is where the code for that is. And then we also have the API documented here, which is how you can interact with the enclave and do that encryption process and then query for matches. And then an example of how you would do that inside of a client application is a very bare bones example is in this repo right here. So just to give you the lay of the land, if you want to check it out, that's kind of where everything's laid out. And so just to wrap up here, whoops, this demo. So right now we basically are running SafeTrace in a single enclave hosted on IBM Cloud. But this is the kind of computational task where we believe that, like, introducing very flexible data privacy to decentralized apps is really useful. And so we think this is a really effective and timely proof of concept for when you may want to use trusted execution environments and applications. For this hackathon, what you saw is kind of where we're at. We have this matching algorithm running. We have the API available, and we're also currently working on building a very bare bones front end that basically enables users to create an account and sign on. But SafeTrace is an API, so some of the things that we would love to see from this hackathon are people who are building other types of contract tracing applications who could benefit from a shared backend and actually match their data with the data from other types of applications. Our backend can be flexible, and we're open to thinking about, what we can change about the data that we're gathering to be more compatible. For example, Bluetooth data. If you are interested in working on additional algorithms that could inside the enclave, that is all written in Rust, and so having any familiarity with that would be really helpful. For example, the heat map project that we discussed earlier in the presentation would be a great project to contribute to. And currently, the individual report is probably just going to be like a list, showing you where you've received matches and kind of just representing that output that Victor received, kind of that Victor demonstrated in the demo. But if anybody has experience, doing working with the Google Map API, so that we can make that a better user experience, that would be excellent for the demonstrative front end for both the data submission process and getting data back. Another thing to just point out, I think we didn't get to it yet, is that our demonstrative front end, the app that kind of illustrates how the API works, is gonna use downloadable Google Maps location history for now, but that could be adapted to any front end that another app uses. For example, like native location data that's gathered by the device itself. Other skill sets that would be really useful to us are people who have experience or knowledge of what's actually useful information to get from these contact tracing apps. I know that the answer to those questions is still in flux, but information like proximity, the amount of time that it's necessary to collect data for, those are types of questions that we've found it's great to hear from people who are actually on the ground and need to use this information. If we are able to incorporate Bluetooth data to get proximity that's not just based on GPS used currently, that would be great. If anybody's willing to test it out as a user or as a developer, we would love that support as well. The project is open source, MIT licensed, and we have both a project management board that kind of shows you what we're working on towards our MVP. If you go here to projects, you can kind of see where things are at. And so if you see an issue here that looks like something you can contribute to, feel free to just comment on it or ask us questions there. And then you can also check out our guidelines for contributing, which are under construction, but can basically provide you with a little bit of a starting point to see kind of what we're looking for moving forward. And so I think that pretty much sums everything up. I'm happy to answer some questions, and I know Victor will be as well. And I think we also have John from our team here too, in case.
Yeah, we can close your video and invite John. Is it okay to invite him to the screen?
Yeah, up to John, I guess.
You can turn off your video. I'll invite him. He can join us if he wants. We met in Berlin at Diffusion a while ago. You can keep your video on, actually. I meant for him if he wants. So I think the first question would be from my side, kind of organizational for the hackathon. We also have James Wall from your team. He's very active on Discord, both your own Discord. Hi John, and the hackathon's Discord. So how do you see people working with you exactly? I'm sharing the Discord channel that we created for Enigma. There's another one for OpenMind and also SafePath from MIT. So what are your ideas? Should they contribute to your project, or maybe start some standalone, maybe forks or related things on their own?
I would probably suggest it depends on the scope of what they're hoping to hack on. If it's something that's like immediately contributes to our project, I would suggest, first of all, it's always good to touch base with us in a real-time channel and just say, hey, I'm working on this. Because there's so many contributors, I think opening an issue for your specific thing you want to do or comment on an issue, making it reflected somewhere in the repo would also be very helpful for transparency. And then outside of that, I'll defer to Victor too on best way to manage that the process of like either merging or separate branches, or whether somebody should just fork the project and then add it. It kind of depends on the complexity and how they're hoping to use the project. So we can handle that on a one-by-one case probably.
By the way, we're doing something, I think it's probably first time ever on the planet for a hackathon. So our Discord, and I think in future also the related GitHub repos are being scanned by SourceGrid. And we have significant token prizes for the most collaborative community members. So the way to get involved is just be active on Discord. For now, we're just running it on Hackathon's Discord. We can add, I think, your GitHub repo and other repos. And every week, I think we'll be awarding around $100 in tokens to 10 people for 8 weeks. So it's almost the same amount as the prize pool. This is not about the money, obviously. It's just to have a way to track collaboration, and tokens are a good way to give people some skin in the game. Maybe Victor, do you have a comment about what's the best way to collaborate with you guys? But you're on mute.
I think that's fine. I think Ainsley covered most of it. Whatever is easy to whoever is collaborating. Obviously we want to make sure that whatever contributions are made find their way up to this repo so that we can all benefit from. But we are very active on both Discord, as you mentioned, and GitHub. So any requests or pull requests that are created or issues that are open, they are commented on fairly quickly. So I think that we will not be the bottleneck for people to contribute to this one, because we are very much interested in getting collaboration from the community at large.
And I would say one thing to add is, like if anyone is building a contact tracing app, if anyone has access to location data or like testing results, we would love to help those teams use SafeTrace as a shared backend. So because of the data silo problem that Ainsley mentioned, yeah, and that's another way that we can help teams that are hacking in the next month.
So just to build on that, like for example, we have a very simple like web-based front end that we're building as a demonstrative interface, and that, as I mentioned earlier, relies on people using Google Takeout to get their location history from the past 2 weeks. It's obviously a pretty bad user experience. So if somebody wanted to build, for example, a bare bones mobile app that just replicated a lot of that functionality, but used the native location data either from Google on device, so people could start collecting it over time or automate that process in some way, that would be like a really awesome hack too.
So I think James is also here somewhere in the chat. Maybe he could write a couple of these ideas. For now, I have at least 2 or 3 related to SafeTrace. You can just list them on your Discord channel, and then we'll try to rally people around these ideas so you get more contributors.
And I will add one thing because like this is the larger data set, the relevant these contact tracing applications become. So like one thing that would be like a success factor for us, or like one thing that would find like a successful outcome is if we're able to, like in hackathons like this, like prove that this is working well, then I'm sure there's so many people out there who are running applications, who are already collecting user data. So then, we could expand the scope of this to everyone who's currently collecting the application. Maybe encourage them to involve a simple survey asking people about their status, and that way we could really, jump or increase the data contribution, because as Ainsley mentioned, like the web GUI we're building is just for demonstrative purposes. The UX is not great, so that would be like a way to take us forwards. So if people know, people who are building applications with tracking data, etc., we should talk on like how we can actually all contribute to this effort.
And this is really the way we want to run the hackathon, more like a privacy-preserving incubator. There are like a gazillion hackathons now running. I think at least 50. So most of them are running over weekends. So we thought this should be longer, over 2 months. We have, I think, close to 40, 50 mentors. A lot of them are experts in cryptography or privacy-preserving AI. So people can, I think we should actually be proactive about this. Also yourself, if we see hackathon projects that are not really mindful about the privacy aspects, we can bring them in, introduce them to one of the projects. It could be Enigma or MIT or OpenMind or Ocean, and we can see how we can help them make them more bulletproof on the privacy side. If you don't mind, it's kind of really late. I think tomorrow it's going to be a huge meetup. We have 210 people registered, so it might go up even more. I think we can conclude here. The feedback I'm getting is people are not very comfortable with the team building activity kind of live on video, so we'll leave that to continue asynchronously over Discord. With that, thank you to
Nima.
John. Yes, John, Victor, and Ainsley, and thanks to everyone for staying with us. You can watch the replay whenever you want on the same link. Bye-bye.
Thank you. Bye.
Bye. Nima out.